Hey guys, today we're going to be working with capacitors and capacitance. Okay, so what exactly is a capacitor? So I don't know if you guys have ever seen one before, but this is a very crude representation of one. Basically, two small wires, and a lot of the times the capacitor in itself is a mix of, I don't know, blue and black, just a little bit. But this is just so you guys can imagine one in real life. What we're going to be working with today is, this blown up model. And if you like, I don't know, just a cross section of a capacitor. Okay. So what it basically is two pieces of metal, which are these two right here. Okay. And they're separated by a dielectric. And this can be, a lot of the times it's, in the example that I was showing down here, a lot of the times that's a piece of paper or something of the sort. But for now, we're just going to go ahead and draw a little box. Okay. So that is our dielectric right there. Now, what exactly is a capacitor useful for? Now, what it's useful for is to store charges. Okay. And what do I mean by this? So basically, in a simple circuit with, these two pieces of metal on each side of a battery, each piece of metal becomes charged, okay? Now, so the right side, we're going to call this one the positive, okay? It gets positively charged since, imagine that there were negatives here before, it was neutrally charged, okay? So the negatives actually go on and travel along this entire wire, and they end up getting stored right over here, which is the negative side. Okay, so now the left side gets negatively charged because it has more negatives, and the right side gets positively charged because all of the negatives actually, quote unquote, leave this side, this one right over here, and they all travel and travel and travel, and they all end up over here. So this is just one charge, but in actuality, there would be quite a lot of negatives right over here, and quite a lot of positives over on this side. Okay? Now, it is important to note that even though there is a change in the, overall charge of the two pieces of metal, both will have the same overall net charge. Okay, so for example, one could go on ahead and have 2 coulombs, and the other would have negative 2 coulombs, okay? So these two are, directly proportional, and how, for each charge, for each negative charge, for example, over here that moved all the way over here, one negative moved over here and one positive stayed here, which is why these charges, are directly proportional and opposite, okay? Now, this accumulated charge on each piece of metal, there reaches a time in which the process of quote-unquote balancing, or the negatives moving over here and the positive staying here, there's a point in which this process of balancing, if you can describe it that way, they will stop, okay? And the accumulated charge on each piece of metal will remain, where they are. Now, it is important to clarify that the charges that are moving are only the negative charges, okay? These are the ones that move freely within the circuit, while the positives are the ones that remain right here, okay? So it's not like there's a positive charge right over here that moves over this way, but in actuality, it's the negatives that are over here. They move over here, and, that's left with positives on this side and negatives on this side, okay? And while all capacitors work in the same way, now, there is a difference in certain types of capacitors, okay? One might store more charge than the other, and one might store less, and the way in which we determine that is by the capacitance of that capacitor, okay? Now, there's actually a formula for this, okay? And, capacitance, we're going to go ahead and represent that with C, I'm just going to write that in the middle right over here. Okay. C is equal to Q, which is the charge, okay, divided by V, okay, and that is the voltage across the capacitor, okay. This is referring to, this charge right over here refers to only one side, okay, of the capacitor, okay, because if you were to take both into consideration, well, the net charge would be 0 as they are equal and opposite. Okay, so we only go ahead and take one, and that's the absolute value of 1. Okay, now the units for this, as you know, charge is a coulomb. Coulomb. Okay, and right down here, this is volt. Okay, and that is actually equal to a farad, in honor of Faraday, okay? So now just to clarify, the voltage here refers to the charge stored in the capacitor, which in other words is the difference in electric potential between the positive and negative charges. Okay, so voltage is the difference, okay, in the electric potential energy between positive and negative charges. I'm actually going to go ahead and put that in a big old square. Okay, there we go. And okay, so a cool fact about this actually is that if you let a battery remain connected to a circuit with these two metal plates long enough, okay, the plates will eventually have enough of a difference in electric potential energy that they will now have the same voltage as that battery, okay? So for example, in this case, we're working with a 9-volt battery, okay? So eventually, these plates will have the same voltage as that 9-volt battery, okay? Now, let's go ahead and try to say that if we were to have a 4 farad, okay, capacitor that stores 10 coulombs, what would be the voltage, okay, of this capacitor? I'm going to give you guys just 1 second. It's, really simple. But we just go ahead and say that voltage is equal to 10 coulombs over farad. And that, 4 farads, I'm sorry. And what we're left with is, we have a voltage of 2.5. Okay? Or let's try just another example. If we had a 6 farad capacitor, okay, that is connected with a 12-volt battery, what would be the charge? Okay, so what we do is we just go ahead and pass this guy over here. Okay, and we're left with 72 coulombs right over here as the total charge, okay, of that capacitor. So I'm sure you guys get the point of what I'm trying to say. It's actually a pretty easy topic once you go ahead and get the hang of it. Let's go ahead and try just one more example. The one that we haven't done. We have, 20 coulombs. It's a massive charge, but that's okay. And we have a voltage of, 5 volts. So that would equal a 4 farad capacitor. Okay. So as you guys can see, it's actually a pretty simple topic once you go ahead and get the hang of it. And one thing that I do want to mention is that you guys might see something called the parallel plate capacitor. Now, that's basically what we have right around here, okay? So what that refers to is these two metal plates, okay? Well, they're parallel to each other, okay? This one and this one. So it just, it's an example of what we already learned, and, it's yeah, basically what we just saw in the video. But I just wanted to throw that out there, I'm sorry, just in case you guys did see something about a parallel plate capacitor and I don't know, you panicked and you didn't know what was going on. This is basically what exactly a parallel plate capacitor is. Okay, so don't you guys worry about that. Really simple topic. I'm gonna write the formula down in big old red so that you guys can see it. So that's C equals Q over V, and this is farad, this is volt, and this is charge. Okay, actually, there we go, charge. Okay, I know I got a little cramped over there, but yeah, that's pretty much it, guys. I do hope that you guys are able to like and subscribe. It really helps support our channel, and leave any comments or any recommendations on how we can improve our videos. And yeah, thank you guys for watching. I hope you do have a great day, and stay tuned for next videos. Okay, thank you.